this might be our local network, like the Wi-Fi, and technically you could also connect via cable to the router, but we don't do that. So these would be our laptops, our phones, and the router, it actually has many jobs at once. Like what we call router, it is actually the Wi-Fi access point and the router and the gateway and something else, the switch. What we are interested in for the purposes of NAT and IP addresses and networking and so on is that it is the router. So the router knows where packets go. If you send an IP packet, which is how all the data basically on the internet is being sent, or how my Chromecast video ends up on this TV screen is also just IP. Many IP packets, they all have a source address and a destination address, and the router knows where to send them to. So if I'm casting, I'm actually not sending it to this Chromecast thingy, I'm sending it to the router, and the router is sending them to the Chromecast. In this case over Wi-Fi. Could also be that I'm sending over cable and then the router via Wi-Fi to the Chromecast. It's all IP. And then we form one internal network. And in this internal network, we all have an IP address. So it kind of depends on the platform, but on Mac you can press Option, the Option key, and then click on the Wi-Fi thing, and then you can find your IP address here and the IP address of the router here. On Linux it should be similar, on Windows it is the same way. And if you want the command line option, you do ifconfig, just ifconfig, and then it will give you like a long list, because a computer usually has many network interfaces, which I'm not going to explain. You will have to find the right one. In my case it's called EN0, sometimes also called ETH0, sometimes Wi-Fi 0. Again, technical detail, and then it will give you the details, the IP addresses of your device, usually in the local network, because you usually are in a local network. What that means, I will explain in a minute. So here, when I click Option and on the Wi-Fi, I only see this address, 192.168.165, which is this one. But there are also others, like these INET 6 lines. They are additional addresses that I have, and they are IPv6 addresses. What that means, I will also explain later. We are going to focus on IP version 4, so kind of the current legacy version of the internet and how IP works. The next version would be IPv6. They skipped 5, but that is more complicated, so we're not going to deal with it now. We all form one network. Like in our Wi-Fi, we can Chromecast and send video to our phones and communicate between our devices. And for this, we always need IP addresses. You cannot send any IP packet without a destination address and without your address as the source address. It is not possible. But these addresses are only valid within our Wi-Fi here. So our router makes up kind of virtual arbitrary addresses and gives each device a virtual arbitrary address that they then use to communicate locally. So in this case, it gave my laptop 192.168.165 as the local address. And if you wonder how to distinguish them from non-arbitrary, non-virtual, actual internet IP addresses, there are very specific prefixes being delegated in the standard as the local virtual ones. So 192.168 is one of these ranges. 10.10 is another range, so you might have seen 10.10 somewhere. This example used 10.0 is also a local range. This is how you know it is local. This address will never exist on the public internet. Like you will not be able to send a packet there, because it is by definition in the spec local. So we have a local network. We all have local addresses. We can send each other packets. We can actually try this. I would encourage someone to do this with me. There is a tool called NAT. It's abbreviated NC. And it's really cool to actually use for this. What you specify is you either let it listen or you let it connect to another NAT that is listening. And then you can directly send data. So I would encourage you, Nora, because you have a computer in front of you, if you are in the little olive Wi-Fi,
yes,
and not in a VPN, to open a terminal,
okay,
and then type NC space and then my IP address. My IP address is 192.168.165, and then space, and then the port, it is 12345. Let's see, probably something doesn't work. So what I'm doing is I'm telling NetCat to listen on a specific port on my computer, and NetCat will do that and receive all the data that my computer gets on this port, and that's just printed to the terminal. It does not more than that. And what Nora is doing, without -L because you don't want to listen, yes, and then space, and then 12345. Exactly. And then type anything and enter. See, this is, Nora just typed this. NetCat actually sent it as an IP packet to the router, to the Wi-Fi router. The Wi-Fi router to my laptop, to port 12345. And then NetCat actually printed this. So if Nora now types stuff, random stuff, whatever, another line, please, then it will show up here. So what?
Private chat.
A little private local chat. And Nora just entered a local IP address. So what we're doing will only work within this Wi-Fi. As soon as she switches the Wi-Fi or enters a VPN or whatever, she will actually not be able to send a package to me anymore. It will fail with some error message. And at the same time, I can of course have many connections open. Like I could do this 1, 2, 3, 4, 6, and now Nina could send me something, or Nora from a second connection. Doesn't really matter.
So one port per another person.
Per another connection, and that another connection can be another person, or Nora could open 1,000 connections from her laptop.
But just one can be.
A connection I will come to that in a minute, but a connection is identified by source address, source port, destination address, destination port. By definition, this must be unique. So what we didn't involve here is her local IP address that she's using, and she's also using some source port to actually connect to me and send data to me. We're not seeing this here, but this is part of how it works. My point was that we can just send arbitrary data over the local network. Like, it does not prevent us from doing it, because the Wi-Fi really doesn't care what we send. If we Chromecast from one device to another device, truly locally, or if we BitTorrent, or if we whatever, send phone, video feed, audio, TV, really doesn't matter. In this specific case, it is not just IP. So IP is like mail pretty much. It's individual packets with a maximum size that depends on the medium. For Wi-Fi, it's usually around 1,500 bytes, so pretty small. And they are not guaranteed to come in order. So if Nora were to send me a letter and IP packets, individual IP packets, then they would pretty likely arrive randomly on my end. Also, like with the postal services, there's no guarantee that they will actually reach me. They might get lost in between, and this is how you notice like the connection hiccups when you have a video call and stuff like that. Then it's actual IP packets just never ending up where they should be for many reasons, like interference with the Wi-Fi, some random, like the CPU of the laptop being busy and not being able to literally receive them while the Wi-Fi is sending them, many reasons. And this is why you don't communicate with IP. It would be really impractical, just like communicating via letters without an order and without guarantee of delivery would be really hard. This is why, so far we have IP Internet Protocol. And this is why on top we usually put TCP, Transmission Control Protocol, I think. And TCP has exactly this job to address the shortcomings that I just described. So underneath TCP sends IP packets. It kind of, whatever you put into a NAT TCP connection, it's also just software, chops it into IP packets and gives them a number, like a sequence, ever increasing, and then sends them. And when they don't end up where at the target, in this case my computer, it will resend them until I acknowledge them. So every packet that Nora sends, she also expects me to send an acknowledgement packet back. And then it does some cool additional tricks to make sure this is as fast as possible, and like that the order still works if there's thousands of packages coming out of order and so on. Effectively, IP is like individual letters, and TCP, if you want a metaphor, kind of works like a pipe, like a virtual pipe. We just opened a pipe between our laptops because a pipe guarantees in order delivery. What you shove in first ends up at the end first, and what you shove in later will always be later. And it also kind of guarantees delivery, assuming it's not leaky. In our case, TCP is not leaky. So what happens with TCP, because it has to retransmit all the packages in case they get lost. So let's say we're having a video call and there's a lot of, you call it packet loss because of bad Wi-Fi, then roughly 50% of all the packages will get lost, and she has to retransmit them all. Like the same packages, the same video that she had already sent before, she still needs to send. So there's kind of congestion going on. So TCP never loses packages. When there's packet loss happening over the internet, over the local Wi-Fi, doesn't matter, it just gets slower. TCP just gets slower. And this is why usually if you have bad Wi-Fi reception, you can still browse Wikipedia and you can still do stuff. The Wikipedia article doesn't magically have holes if you fetch it. It will still be complete, but it will take a long time to load, because TCP makes sure that there's never stuff missing at the cost of speed and at the cost of performance. And there is another thing we can put on top instead of TCP. Wait, what's going on here? On top we can instead put UDP.
So one question, this what you used now to communicate with Nora, was this just IP? Or was this already TCP?
Yes, sorry, I should have introduced NetCat after explaining TCP. NetCat does TCP by default if you don't set anything else. So what Nora did, she opened a TCP connection to me on port 12345 from her source port to my destination address, destination port. So there's lots of IP packages flowing pretty much all the time, even just to keep it alive, the pipe. But from the top, like from how we are using it, it looks like a pipe. So it's abstracted to look like a pipe. And that's why even if you were to send me a giant file, you could now pipe a giant file, or we can do it the other way around actually. I will show you. I will jump to my downloads folder.
But she's not listening.
Yeah, we will do that. Or I can show it on my laptop, but it's not as impressive. It still should work. Just it doesn't matter if it's sender and receiver on my laptop or sender on my laptop and receiver on Nora's end. Just keep in mind that it's the same thing. They will still go once to the router and then come back to my laptop. So I have some file, whatever, like this thing. This file is 16 megabytes. Yeah, cat pictures, I would have to download one. You can send me one, then I can show you a cat picture. And I can cat that. What cat does is literally, well, it reads the file. It literally, cat does nothing else than reading the file and writing it to std out. So kind of like the output of the process. And then we take that output and connect it to the input of netcat. This is what this thing here is for, this character.
So if you would just run cat it would print it here. We would see it.
Yeah, print, but printing it, well, it's a jar file, so it will be arbitrary garbage.
Yeah.
If I were to print a long text, we're going to do something. So we're going to send a lot of random characters. So I'm going to, this first thing reads from def random, a never-ending, ever newly generating random sequence of random bytes. It's basically a virtual file that is never ending and never empty. So I'm going to read 10,000, 100,000, a million actually bytes, roughly a megabyte, right? Random characters, and then encode them as hex, and it looks like this. It's really a lot. Like it's a million bytes encoded in hex. Someone can calculate how many letters we're seeing. A lot. And this is my file, random.txt. And now I have a file, random.txt, 1.9 megabytes. And I cat that file. If I were to cat that, I again get the random content. But at this time, I pipe it into netcat, into the input of netcat. And now Nora would have to listen on her machine using this command and then make up any port. Can be really anything above 1000 for technical reasons. Dash L and then make up any port number, any high port number.
2, 3, 4, 5.
2, 3, 4, 5. Okay, and now I still need your IP address.
So is if config.
Yes, and then space en0, or if you're on Macs, tap option and then click on the Wi-Fi symbol, and then it will show here.
Can you do tap the option key?
Wi-Fi setting.
Now press Wi-Fi. There should be somewhere IP address.
Yes. 192.1.7.2.
7.2. Okay. So you now have netcat listen running, I guess. I guess sometimes it asks for like the firewall to allow this or something. In this case it doesn't. Let's see if it works.
It works.
Yeah, so there's 1.9 megabytes of random hex characters showing up at Nora's place. And this way we have demonstrated that we can pretty much shove anything into netcat. It doesn't matter. It doesn't bother with what we're sending. If we're manually typing hi or sending random characters, I could send you a cat picture if I had one now. It really doesn't matter. Yeah, it doesn't matter. So now we did a TCP connection. We can do a cool thing. We can pipe the file into SHASM, and it will create a hash from the input data. And if Nora has the same hash, like pipes netcat's output into SHASM, then we will know for sure very, 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 very likely that we have the exact same data. Because if the hash is the same, the data is very, very, very likely the same. So you would have to run the netcat listen command again, because netcat just prints it out and then forgets what it has received. So I will have to send it to you again.
Okay.
And this time pipe it into SHA-SUM first.
So you do listen space pipe.
SHA-SUM. SHASUM.
Like this.
So what hash do you get?
Ending 8B05.
Yeah, 8B05. So
Start
if we were
with
to read
the-
this entire thing, we would be extremely likely to have the same data. So we just made sure that we can successfully send 2 megabytes via the local network. Now we can do amazing stuff.
And we proved it also.
There's a tool called PV. All it does, it takes the data from the input, directly writes it to the output again, but it also tells us how fast data is flowing. So let's say I'm continuously reading random data. It doesn't really matter from where. I could also read endless 0 bytes. This is a special file that endlessly contains 0 bytes. Really doesn't matter. And then I pipe it through PV to see how fast data is actually flowing through. It's pretty much as if you had a pipe and on there was like a small meter showing how much water is flowing through, to stay with our metaphor. And then I'm sending it to Nora again. 722345. You need to listen again.
Okay.
And remember to send this data somewhere. Otherwise you will end up with lots of data in your terminal. Like you could do it, but it will like really go crazy.
I have it because it's
So you can redirect to the unofficial trash called devnull. Devnull, right? So it's a greater than character, and then /dev/null. It's a special file that whatever you write to, it will always be null, as in 0. Null. N-U-L-L. Yes. So if you do this, whatever you receive will immediately be deleted. But our whole point is of just measuring how fast we can transfer data between our computers.
Cool.
So you can start it.
Okay, I started.
And now we can see that netcat can only send it as fast as the Wi-Fi allows us to. So PV can only shove it into netcast as fast as the Wi-Fi allows it to. So this number represents how fast the Wi-Fi really is between our computers under these conditions we have currently. So we can see that we have by now sent 100 megabytes of random data to Nora, only for her to throw it all away immediately. And we're currently sending at about 4 megabytes per second. So times 8, then you get the megabits. So we have roughly 32 megabits of bandwidth in this Wi-Fi available. This is, of course, all depends on how many devices are there, how far we are away from the router. I could actually now move away, and probably the bandwidth would eventually...
Wow. My streaming got blocked by...
Oh yeah. I will explain in a minute why.
So we're not recording anything.
Oh no.
See, it's getting slower.
Yeah.
500 kilobytes per second.
And less reliable, like it has more variance.
Yes.
So we can see we have successfully, using just command line tools and the concept of TCP and IP, measured how fast our Wi-Fi really is, not how fast it claims
Stop
to be.
it so we can start recording again.
Sorry.
Now it's literally, and we're back.
So what happened is my device was trying to shove this data over the Wi-Fi. The router was trying to shove the data to Nora's laptop, and also Nina is streaming over the same Wi-Fi. And because of how Wi-Fi works, by definition, we all have to share the bandwidth. It is literally not possible to send at the same time. So what the Wi-Fi smartly does without us noticing is divide basically a second, if you will, into 4 shares now. In one share I send, and the next time Nora receives, then Nina's phone sends, then Nina's laptop receives. So if we're taking, with 2 laptops, a lot of shares of the pie away, then there's not much left for Nina's phone and laptop to actually record properly. So this was all local. We could have a thunderstorm and our Wi-Fi router could be entirely disconnected from the public internet. It doesn't matter because it's all local, because we're using, by definition, local IP addresses. And this is also how peer-to-peer software, if it has built-in support for that, can find each other locally over some mechanism that I might explain later. Let's see if we come to that. And then exchange data locally, because in fact often it's much faster to exchange data locally and much more bandwidth efficient, and if you're tethering with your phone, you don't use your data up and so on, than actually sending it somewhere to the internet and back. Okay, so back to the NAT topic. All we did so far was here. So Nora's laptop was basically this one, and this was mine, and this was Nina's phone, and this was Nina's laptop, and they were all constantly sending to the router back and forth, us random crap, and Nina actual video content. And what if we want to send something to the public internet? And for this, I'm going to, I guess, log into a server of mine.
You can also switch to another Wi-Fi if you will do a lot of data transfer to the wizard.
Yeah, I will keep it low. Actually, this PV tool that I showed can also be used to limit the throughput. So if you only ever want to download 100 kilobytes per second, you can pipe your command line tool through it, and then you will limit it. So on my server, it has some kind of public IP address. I will explain that in a minute. I'm going to do pretty much what Nora did before. And then I will connect to it. Let's kill this. Like this. NC. I need to find out the... no, I can actually do it this way. So this is the address of my server. I will explain that. So I successfully just sent data from my local computer to my server called Elm. And on Elm, I started netcat in listening mode on port 12345, and it has successfully received hello. I can also send data back, by the way, we didn't do that yet. So I typed in elm.jannisr.de. This is a domain, and a domain is resolved using the DNS. And you can use the command line tool called dig, like shoveling, to actually find an IP address. This is how, by the way, exactly the same thing what happens if you enter this in your browser. So if you enter elm.jannisr.de, it will do the same thing, exactly. So we successfully got an IP address. This is the IP address of my server. So instead of putting the domain here, I can also put the IP address here and send random data, and it will end up here. So I can demonstrate it works. And this address is not a local address because my server is not in this Wi-Fi. It's somewhere in, I guess, the Netherlands or something. So it needs a public IP address somewhere in the internet, usually just shown as this globe or some random cloud, but it's made up of many different individual paths where IP packets can travel, and made up of many different routers in between. I can also show that later, but let's say there's some path to the IP address 543.775.136 from our local router. The problem is I cannot send this with, in my case, 192.168.165 as my source address, Because if the server were to respond, I would never receive the thing back, because it's by definition a local address. It's pretty much as if you were calling within the same house and saying, kitchen here, can you come to the whatever, let's meet in the living room. If I would do that over the public internet, no one would know where kitchen is. So it's like by definition local. And this is why I need to send this packet to the router, and then it actually needs to put the public IP address of our internet connection. So its public IP address in the source packet, in the source address of the IP packet. So it kind of unpacks my IP packet, puts in the public address, so on the public side, kind of the road-facing side, it has a public address, and then sends the packet on. And when it gets the packet back, the destination address will say our road address. It will unpack it, put my local address again, because it remembered that this belongs to me, the response address, not to Nora's laptop, and send it to me. And I will receive it as if 0 routers were in between, or 0 such devices and repackaging were happening, or 1 or 2 or 20, it really doesn't matter, because I send it to the Wi-Fi router, assuming that it will work, and it will repackage and then send it on. And this is called network address translation. So network address translation we usually never notice, because all our IP packets that we send are magically being repackaged by whatever device is doing NAT, very commonly the router, the Wi-Fi router.
How do we find our public IP address?
This is the tricky part, which is, by the way, also tricky when doing P2P applications, because there are 2 peers. They would like to communicate to each other, but they really can't, because they don't even know where they live, so to say, on the internet. They don't know their public addresses. As if you were trying to mail to Nina living somewhere, Nina CO, wherever you live, and then the address, but I don't know where to write that letter to, actually. I know that I want to reach Nina, but where? And the common way is to actually ask someone else, to actually, like send some data to a server. It will look at the source address of the IP packet, because every IP packet has to have an source address, and give that source address as data back. So create a response with the source address as data itself. That is literally what such services do. So if I go to whatthefuckismyipaddress.com, of course in practice it sends much more. Like it sends an HTML page with like red text and links and white text and IPv6 addresses and many things, but in fact it really doesn't do anything else than looking at the source address of the packets that I send it. So technically, what I did here is not ask what my laptop's IP address is, public IP address, but this house's public IP address. So if you were to do this on your laptop, you would actually get the same IP address. Because from the outside, we all send it from one Wi-Fi router with one fiber optic connection with one public address. As if we were all sending mail from this house, it would have one regular street number and street on the envelope. So this whole metaphor fits quite well, the letter metaphor, in the way that there would be some person getting the mail from the outside, like the response mail, and then checking, yeah, right, this belongs to Nina, this belongs to Nora, this belongs to Alex.
Our names are ports.
Yes, our names are ports. This is how it works underneath. It remembers which response package belongs to whom using ports. So we covered network address translation. This is of course a problem to peer-to-peer servers, as I said, because they can't just connect to each other. And this is why you usually do hole punching, which is very complex, but so I'm not going to explain this in detail, but the basic idea is always you have someone on the outside helping. Some server that is publicly available on the internet without NAT that I know how to connect to, whatever, the Google server or my public server, it doesn't really matter, anyone's. And there's a thing running helping me discover how to make a connection to the outside. And then you would kind of connect that connection to the outside to someone else's connection to the outside, like plugging two pipes together. So Nora Nora's in Taiwan and connects to this public server and has a pipe to the server, a TCP connection, and I connect to the public server and have a pipe, and then it would connect our pipes together and not interfere with it anymore. That's pretty much how hole punching works. There are like many details that make it more complex, but that's the gist. Any questions so far?
So this NAT, network address translation,
Yes.
Public IP. So to figure out my public IP, I send a message out, and then the receiver can see where it came.
What it was on the envelope,
Yeah.
kind of. Yes.
Okay.
Because from the inside, there's no way of telling. You could also, another possibility, go to the admin UI of your Wi-Fi router, because it has to know, right? If your Wi-Fi router does NAT, so it has to know what to write as the sender address. There's literally no other way. So you can look in there. So if we had access to the Wi-Fi router and there wouldn't be like a password in the way, we could actually do it this way too. And there's actually smart protocols how devices in the local network can, via an API, ask the Wi-Fi router what their public IP address is, but it's unfortunately not widely supported. And it would make hole punching so much easier and many other things so much easier.
And it's also
than
not
it is.
written on the router.
No, because it's dynamic.
It can also change.
Because in fact, what happens if your router connects to the internet, it actually connects to the ISP, and the ISP assigns some IP address. And often it reassigns the same again. Like if the connection were to cut out because of thunderstorm and we were to reconnect 30 seconds later, we would likely get the same, because then we disturb very little. But it doesn't have to. It can technically also get an entirely different
But
one.
it would be cool if routers had like a display to always display what is currently the IP address or something like that.
Would be very cool, yes.
But that's why you can connect to the router through.
Yeah, it's like a very complex mechanism, if you will, just to find out your public IP address. Usually it's the easiest, although it's kind of random, to just send data somewhere and ask what was on my envelope, like what was the sender address of the IP packet. It's kind of a hack, but it's very effective. This was IPv4. And IPv4 addresses have 0 to 255, so 256 possible numbers in the first place, 256 in the second, third, and fourth. So we have 256 to the power of 4 possible addresses, which is roughly 4 billion. Because back when IPv4 was designed decades ago, people wouldn't think that the internet would ever have more than 4 billion devices in operation. So they designed it that way, also because of computers were like not powerful enough to have longer addresses. Actually, like this was a performance optimization to only have 4 billion possible addresses. Keep in mind that the devices, there's just this globe displayed. It's of course not just one thing. It's a giant network, and there's many routers in between that all have to know where to send the package. This is how the internet works, right? They just know, oh, this package belongs vaguely in East Asia. I'm going to send it this way. And then the next router knows if it belongs to Japan or Taiwan or whatever, and then sends it further. All those routers have to have giant routing tables. So back then they were designing it with 4 billion possible addresses, which is why we have a problem nowadays. There are more than 4 billion devices, actually almost more than 4 billion devices online at the same time usually. So we could not, let's imagine this wouldn't exist, give each device a public IP address. For many other reasons we also don't do this, but we cannot. So we kind of need NAT, and actually to have more than 4 billion devices connected to the internet at the same time. It wouldn't work otherwise, because things break horribly if two devices share one IP address, because then letters might ending up in the wrong destination. This is kind of why we're locked into NAT currently with the old IPv4 legacy system, if you will.
So NAT means that we have public and private
Yes.
addresses.
As soon as you have, or private addresses means that you have NAT, but yes, like as long as you have private addresses, you need to translate them somehow into public ones and do NAT. And we have private ones because we have more than 4 billion devices.
But because otherwise each computer would have its own address, each device.
Could. This is what it was back then. Like you were literally plugging, there was no Wi-Fi, you were literally plugging your workstation, extremely expensive workstation machine, into the Ethernet jacket of the university, and very likely, and manually configuring things, because things didn't like automatically work back then, but you were having a public IP address. And this would have many benefits, especially for peer-to-peer applications, because what Nora and I just did locally, you can then do via the internet. Like it really connect from server to server directly, as if nothing is in between. Screen sharing, calls and all this stuff would be way less awkward, and there would no centralized services be needed. You could actually, if you want to send some data, like this common problem, I took a photo and I want to send it to someone, you wouldn't need some stupid cloud services, because you can literally directly send it to their IP address.
Even from remote.
Even from remote. I mean, it really doesn't matter where it is. If it's my neighbor or if it's Nora in Taiwan, it really doesn't matter, because it's some address that I can reach. But we can't, so we have NAT, so we have problems. It actually also has some benefits, like the router is pretty unattackable, because it's a very simple device. Not unattackable, but it has less attack surface, whereas a laptop has like a huge amount of software, so it's much more attackable. So there's kind of a security angle to that, but not necessarily that one needs NAT to have secure computers, just that it coincidentally helps us be secure. For example, if we had no NAT, this Chromecast would definitely have a password to connect, because otherwise literally everyone on the internet would be able to Chromecast to our TV, and thousands of people at the same time, like stealing the connection and so on. So you would have to design software very differently if there was no NAT, but this is no good reason for NAT to exist. IPv6. So if you do ifconfig en0, luckily we are in an internet connection that has IPv6 support and a Wi-Fi router that has IPv6 support. Basically every device nowadays has it. Maybe like your, I don't know, Wi-Fi alarm clock doesn't have supported for it yet, or your fridge, but mostly every device has. So I have an IPv4 address, kind of the old addressing scheme, and I also have more than one actually IPv6 address. So I can also be reached via the IPv6 address. So this whole netcat dance that we did with Nora and I could also be done via IPv6 addresses. It's just as possible. As you can see, they are much longer. So they are hexadecimal, and each group can have 4 hexadecimal characters, and there's 8 groups, so they have enormous amounts of addresses. For every square millimeter of the planet, there's billions of addresses. So enough. And actually your device could not just have 2 or 3, but a billion. It really wouldn't matter, because there are so many that it doesn't matter. IPv6 is slightly different and more complex, but it also has the concept of local addresses. Some addresses, like this prefix, I think, some of this means that it's a local address by design. And this one actually points back to my computer. Like this is by definition not even going to the Wi-Fi router, but just within my computer back to myself, kind of, called loopback. So most of the features of IPv4 are actually also available in IPv6. So you can tell from an address, is it intended for the public internet or is it a local address? IPv6 has so many addresses that we wouldn't need NAT anymore. So if the Wi-Fi router here would let us, we could actually use this internet connection without NAT. There's no reason for us as P2P developers and people who can take care of the security of their laptops, hopefully, to have NAT. Really, it doesn't help. It goes in the way of many things. So if we had the option, we could turn it off. Mostly you don't have control over the Wi-Fi network, so you can't. But at home you could theoretically try doing it. Then you lose, of course, IPv4, because with IPv4 this doesn't work as I explained. So you're IPv6 only. This is a major caveat because there are some services on the internet that don't support IPv4 yet, IPv6 yet, like Google and all the modern, services, cloud service, they all support IPv6, of course, but like your local library around the corner might not, like their server, their website, or whatever. Some supermarket chain might not. But you could theoretically do this locally. IPv6 has so many addresses that theoretically, unfortunately it doesn't. Our Wi-Fi router could have billions of public IPv6 addresses. It actually gets many, many billions of IPv6 addresses at once from the ISP. So it gets just one IPv4 address usually, but billions of IPv6 addresses. And it could give like 1,000 to each of our devices, public IP addresses. As in, we could actually use them to send packages to the public internet, and they would actually directly receive at our end again without NAT, without translation of addresses. Would be possible, unfortunately is not very common. Let's see what happens if when IPv6 finally becomes more common.
Who decides about that?
It's a very complex thing. Technically, everyone can use IPv6 right now, like the internet, if you will, supports it. Like every major ISP, every internet infrastructure supports it. Every major cloud provider supports it, but usually people are lazy and implemented IPv4 only, which is sad because it would have a lot of potential. So in fact, who decides it? It's kind of the group of all the people who write software that does networking. And if some major software doesn't support it yet, let's say the fridge doesn't support it yet, if you were to turn off IPv4 in our Wi-Fi router here, then the fridge wouldn't have an internet connection here anymore. If that's important is a different question, but like I'm pretty sure that pretty much all embedded devices that still connect to the internet don't have it. Like some weird IoT smart lock, some whatever enterprise machinery in a factory doesn't have it, and so on. So we covered IP, IPv4, IPv6. We covered on top TCP. So IP is just letters, and TCP is pretty much like a pipe. It guarantees the order and that messages actually end up that they actually get sent. And I guess some other cool stuff would be, so 1.1.1.1 is a public IPv4 address. It's not local by the standard, so it means it's somewhere in the internet. It belongs to a company called Cloudflare. You could also pick any, really. This belongs to Google. And there's a practical tool called traceroute. And what it kind of does, it sends empty, meaningless probing IP packets just to find out where and how they travel through the internet. So if we do traceroute 888888, and then it prints that route, like that path devices took through the internet and the latency. And from the latency, we can roughly estimate how far it is, because the internet is pretty much roughly fiber optics, which is pretty much roughly light, the speed of light. So we can roughly calculate how far things are. Of course, the CPUs in between, like the devices, internet infrastructure devices, create latency, but that's like a detail. So we start at my computer with 192.168.165. That is not printed here. It's kind of the hop 0, if you will, on top. And then the first hop that our packets take is 192.168.1.254. This is our Wi-Fi router. It's also printed here. This is where we send all packages, even if we communicate locally or if we communicate to the internet. They end up at the Wi-Fi router. And we have a latency. I think this is like something like 3 measurements or something of a few milliseconds, like 2 to 3, maybe 4 milliseconds, because it's local. It's somewhere around here, so it's quite fast to transmit it. And then we make a big hop and actually have almost 8 milliseconds. So assuming there's no CPU causing delay, quite far actually. It might be in Lydia, for example. Could very well be that that is the next hop. So there's some device with the public IP address 10.234.641 in this hop. And then we go further and further and further through the internet infrastructure. So the first one might be our ISPs, like the gray box in the street, you know, that might be the first hop here. And then the next one would be in some data center in Lydia. And then the next one would be in some data center in Lisbon. We really don't know because it doesn't tell us. But eventually, this is, I guess, some internet company. And eventually we end up at Google in Lisbon, I guess. So we're 25 milliseconds, 24 to 27 milliseconds away from Google, and we kind of find out the path in between. In this case, it's quite boring because it doesn't tell us much. It just told us random IP addresses between us and Lisbon, pretty much.
You could ping your server.
I could ping my server.
I'm sure it's right.
The reason why there's delays in between and why there's these stars, because not all hops, not all devices in between actually say what they are. They may just forward packages without responding to my special probing packages. They might not tell what they are. But we can see that the first path, the first hops, actually the first 6 hops are pretty much the same. Actually down to the IP address, hop 6 is still the same, and the latency is maybe slightly different, a bit slower, but still the same. 13 milliseconds to this weird thing here. So it's probably somewhere in Portugal. And from then it took a different path. It goes to this thing, and eventually, hopefully, it will end up, I don't know where my server is actually. France, Germany, Netherlands, I don't remember, something like that. Yes, so it ended up somewhere in France.
Before it was Spain.
Yes, exactly, somewhere in Spain, and then somewhere in France, and then somewhere in Germany actually, in Frankfurt, with a latency of 54 milliseconds. And this is how those probing packets that this tool sends kind of travel through the internet, so that you can debug this. This might of course change at any time. It's like highly dynamic, and if they reconfigure something or it's a different time of the day, it might be different, but it's interesting to debug where the problem is. If you send a trace route to whatever, this one, which is Google, or a good start is to traceroute.google.com because it's available anywhere on the planet. And if the first hop,
maybe not in China.
maybe we could see, it would be interesting. You can look it up. There's databases of tools regularly doing this and uploading this, so one can have like a world map of how the internet is connected, and there's cool stuff.
One question before, when you were sending something to your server, it went like super fast. But now when you're running traceroute, it takes forever. Why?
Because it waits for the device to respond. Remember that I'm not sending normal traffic, as in just forward my traffic wherever it belongs. I'm kind of sending some meta packets. Tell me who you are.
So they have to
I'm sending special packages, and these packages, for technical reasons, have a low priority. So it might be that these devices are very busy handling actual traffic, and this is why by design those meta probing packets have a low priority, which is why traceroute by default waits extremely long, like 10 seconds
Especially
or
in
something,
Frankfurt, it's waiting forever.
to actually get something back. And likely there's not more
It's busy, man.
happening.
We were many times in Frankfurt, we know how they
Likely-
work. They're like pretty much.
Likely there won't be more, you know.
Probably,
like-
probably a problem with security.
So it might be that the next device is just configured to never reply, that we don't know. This all depends on their cooperation.
So dots are waiting, or
Dots are no
unknown.
reply. So one reply, one request with no reply.
So that's
Second
what they do in
request.
Frankfurt, Alex. They don't reply. No,
Yeah.
Frankfurt reply.
Frankfurt, something in Frankfurt. I mean, like this is Limburg, I think. This might be the one company that forwards data to the other company, and technically it doesn't have to tell what it is, right? They can name it whatever, but because it's practical for system administrators and networking people, and what we're doing, also networking professionals do, it's really practical to know what 195.8.126 actually is. So you give it a somewhat useful name. You know that it belongs to some company, probably Portuguese networking thingy. We could look it up. And they give it some name, probably the data center, and then the rack in the data center and the actual machine, to know which machine actually forwarded or replied to our kind of special program.
And those
probing
who
packet.
don't reply below, we know that they are devices. So we know that, like now it ended. So
I
so we
cancelled
know.
it.
Yeah. Okay, but let's imagine that this was the last one. We know that from here to your server, that will be 28 devices.
No.
Uh-huh.
If there was one actual successful line at the end now, then we
Yeah.
would.
Yeah, that's what I mean. Yeah.
But you know, as soon as you can't see further, you don't know if it's another 3 hops or another 10 hops. It doesn't
Yeah,
tell you.
but we know that 17 is a device.
I don't know. We know that 14 is a device, and we know that it's not my server yet.
Yeah.
So there's at least 15 devices, but we don't know. It could be another 100 devices.
But it could be just one.
Could be one. Nobody tells us anything, so really don't know. In
And
this
then
case,
we try again. Maybe we're just trying again, or what?
maybe, but it's unlikely. They're probably just configured in an unhelpful manner, so they don't tell us what this is. There's many reasons to do this, like
But maybe it's
spam,
only
for
security.
example, security DOSing. Like you could send trillions of those probing requests, and maybe for performance reasons or spam or DOS reasons, they actually turn that off. Who knows? Maybe it's just wrongly configured, and I configured my server the wrong way. Could be. In any case, this already tells us a lot. For example, if you are on a shitty Wi-Fi, you do traceroute to Google, and if the first hop is already slow, every Wi-Fi does NAT in practice. Technically not required, but pretty much any Wi-Fi does NAT. And if the first hop, like the local device, in this case called DSL device, it's our router, already has an extremely high latency, then you know it's somewhere between your laptop and the router, likely the Wi-Fi itself. If it's somewhere after, like in our case, the Wi-Fi connection isn't exactly fast for Wi-Fi, you know, like 1 millisecond is okay, but it's in an okay range. If this was 100 milliseconds, then we should worry. But in our case, the latency adds up somewhere after. So this is like likely, I know that Google is in Lisbon. I just happen to know this. You would have to pick a server where you know where it actually is. We know that the latency adds up somewhere behind our Wi-Fi router, so without our outside of our realm of control. It's just how the internet works somewhere here in Portugal. If you were to do this in Taipei, it would probably not be 26 milliseconds, but somewhere around 10, because it's fiber optic and very fast and very modern. And we also know other stuff, like where it goes to, and if there was my server responding, then we would know that there's 0 to an unknown number of hops in between that don't say what they are. So this is kind of a rough debugging tool that helps us get a rough idea. if there was 2 NATs going on, you can technically put double NAT. And this happens. Half of India is actually connected via double NAT. And this is really a problem because we try our P2P solutions and we take into account NAT and we engineer around that and we build hole punching and so on with 1 NAT in mind. And then there's India, where basically this is the Wi-Fi router, and then there would be another such device in huge from the ISP in between. So every house still has a local address that is local to the entire ISP, and then the entire ISP has 1 public IPv4 address. This is problematic for many, many reasons. Like if one computer does shit, then the entire ISP's IPv4 address will be blocked for spam and so on. Like it's really shitty. But Indian internet users can't change much about this.
And why do they have it like that?
Because they have so many addresses, so many people, and historically they have been assigned such little IP addresses. I can explain that in a minute. So you have double NAT, and if your software can handle that, because it's a really tricky thing when programming it, then your P2P solution just won't work with those ISPs. And then traceroute would show us 2 local addresses consecutively. 1 in the local address, in the house local address, and 1 in the ISP local address. And this is how you could tell. You could use traceroute to actually find out there's double NAT going on. This is called carrier grade NAT or CG NAT, when the entire ISP, exactly, so there's 1 local network and then there's big local networks done by the ISP.
That's in India.
It's in several places, big whatever corporations I guess do it too, I don't know, but it's as far as I know, I'm not sure, like most of the users actually connected to the regular internet that have double NAT are in India. The IPv4 address space, I mean, it can be just one ISP randomly assigning an address to our router, and then the same address being used somewhere in Taiwan by their ISP and assigned to their router, right? Then chaos happens if 2 places have the same address, because suddenly packages wouldn't end up where they belong. So you have to make sure that no address is used twice. So what they historically did, they divided the entire range of IPv4 addresses, those 4 billion addresses, into sections. And they said, this section belongs to Europe, and this section belongs to Africa, and this section belongs to North America, and so on and so on. And they did that, I think, in the 90s or something, based on how many devices were available in each region back then. And since then, like China and India have really exploded in the number of devices. So there's historical, notorious pressure and low availability of IPv4 addresses. And there's a market for IPv4 addresses, and which is why they are worth so much, because ISPs really want to buy them in order to be able to give out enough. And in Europe, they're actually used up. You cannot buy them from the central or obtain them from the central registry, obtain new ones, because there aren't anymore. It's like the first place where they are not available anymore, and you have to buy them from other people willing to give them away. So it's now kind of a regular market, which makes this very expensive. I mean, this is part of why our internet connections are the price, because ISPs have to buy the IPv4 addresses. Okay, any questions?
So we could resolve this problem by upgrading all devices to use IPv6. That would be a solution.
Yes, you could. Exactly.
So if governments, for example, would make grants for all the devices to be upgraded,
or regulations. Like
Or
they
yeah.
can actually, there is like a label that you need to have if you're like an internet device in wherever, pretty much Europe, and then there's a label for Asia and then so on. So they could pretty much just make a rule from 2025 you need to support IPv6, and then we would have to wait, I guess, another 10 years until all the old devices are out of service, and then we could finally turn it off. And there's an entire Wikipedia article dedicated to just this strategies
Cool.
and limitations and countries' progress. And Google has like a page how much traffic is IPv6, like this one, because they want to push this because they benefit a lot from IPv6. Actually, not as slow, right? This network address translation, it's usually not the limit, but it's some limit on the way. Like it creates latencies and makes things more complicated. And there are many other disadvantages of NAT. So Google has an interest, and that's why they continuously chart the amount of IPv6 traffic that they reach. And actually this pattern is because some devices have more IPv6, and like enterprise devices usually have less IPv6. So you can basically tell which countries are currently online because countries with more IPv6 pull up the curve, and when they sleep, the average rate of IPv6 traffic goes down again, because it's the global average of all the traffic of all the countries. And that's why there's this pattern, because different countries have different ratios. It's really quite different. So for example, where we are, Portugal has 37, whereas Russia has 6. So really makes quite a
Percent.
difference. Yes, of the traffic, not of the Google requests, but
No,
of the
but
traffic
of all traffic in Portugal.
that Google receives. And Google is quite big, so it's kind of a good indicator for the entire.
So who has the most? Can we check Taiwan, for example?
So Japan is a lot. Taiwan has 54 almost, or 53. India has 70 because they have so little IPv4 addresses. I mean, even the ISPs don't want to do double NAT. It's really pain. Like everything's broken. Why does my phone call not work? Why does my Discord call not work? They get support requests and so on. So they have an interest to push IPv6.
What about Germany?
Germany has historically had quite a bit because I think because a lot of networking standards are being co-developed by German people and Deutsche Telekom and so on, which is why I think it is the case.
What about US? Very low. What about UK? Sorry. Also low.
Oh, China.
Actually, just 5. I wonder why, because they have many people. I don't know how they do it. Like how they have 1 billion people.
Maybe
I'm
have
sure they
IPv6,
don't.
But they have the.
Maybe they do
Firewall.
double
Yeah,
NAT. Yeah.
Internal
Yeah.
IP, I don't know.
They have the firewall. Technically, firewall is something else than NAT. Usually it's combined. In this Wi-Fi router, it's combined, a firewall and NAT. But technically, it's two different things. You can have a firewall without NAT, and you can have NAT without a firewall. But it might be that if they're already building a national kind of firewall filtering, firewall is kind of a wrong, like a euphemism, censoring infrastructure, build this, then why not build NAT in, with all the
Chinese like to
disadvantages.
build walls.
I don't know. We would have to research this. There's separate sections for each country, so you can look into how things are going. But this is kind of out of scope. But NAT is the reason why WebRTC, the browser P2P connection framework, has this whole weird stun thing and this turn thing as a fallback if stun doesn't work, for hole punching, because NAT, that's the reason. Yeah. So I'm gonna maybe show one more thing. and then you might be tired. I'm not sure if this Wi-Fi allows it. So traditionally you send IP, as I said, is letters, right? It's IP packets like single boxes or letters, really doesn't matter. They have a sender address, a receiver address. And you send it to one specific address and it will be routed exactly there and maybe hopefully delivered if there was no packet loss. And that is the common way of sending things, because you usually want to send stuff to one computer on the network or one computer on the public internet. That's the normal way, and this is called unicast, because it's one device. There's also a mode that is called broadcast, where if you send to a specific address that is like a special address and it's defined in the standards as the special address. So if I were to send this to the Wi-Fi router with this special address, the Wi-Fi router would actually send it to everyone in the network. And this is a traditional thing. It was back then a performance optimization. If, like, remember, computers were extremely slow and there were very little, maybe 20 in an entire university. So there was an optimization. If you wanted to send something to every computer, like an update or something, you just send it as a broadcast to the broadcast address called broadcasting. And then it would end up by the network device being copied, kind of replicated to all devices. And it's an optimization. You can maybe see why this is a bad idea, allowing this on the internet. You know, if someone sends a thing and it ends up on every device on the internet, like billions of devices. So this is not allowed on public internets. On the public internet. This is only allowed within local networks, and local networks don't have to allow it. Actually, if you go to an airport with like 10,000 devices, I'm pretty sure that broadcasting will not be allowed and will be suppressed. Just this packet will be dropped and ignored by the airport Wi-Fi, by the router. And there's another smarter mechanism that is also usually blocked in an airport, but usually allowed in a local network, called multicast. So it means not for everyone, but for those that are interested in receiving it. So it's kind of a subset, more than one device, but those that are interested in it. And there are special special IP addresses or ranges of IP addresses, IPv4 addresses defined for specific tasks. How do I explain this now? Most of them are pretty like random and technical and not interesting for us. But there's some, and I actually don't know which one. Wait. That we can use to do cool stuff. For example, this one, 224.00251. Might seem completely arbitrary. It is completely arbitrary. They picked out of those special addresses one and said, we're going to use this. And then they built a standard around this called multicast DNS, where devices can say to the local network, I am in the local network, I am called Jannis laptop, and I have IP address X. And they send this to the multicast address, so the Wi-Fi router will efficiently send it to all other devices interested in this kind of information. So even if there's 50 devices, I don't have to send 50 packets to communicate this. I just have to send one, and the Wi-Fi router will take care of the rest. So it's like quite efficient compared to other ways of doing it. And I cannot just say I'm Jannis laptop, my address is X. Then others know, by the way, a human name for my IP address. They know a human name for many IP addresses, in fact. So if you use one of those network scanning things, these There's lots of upgrade to Pro because I didn't pay for this tool, but these are all the local names that these devices send via multicast in the local network. This is like a Mac tool, but you can use this. There's a Linux tool for that too. And on top of that, there's something called DNS SD, DNS Service Discovery, where they don't only say, my device, I'm called Jannis laptop and I have IP address X. I also have a printer available for the local network, or I have video Chromecast stuff available, as in you can Chromecast to me. I have a Chromecast service running on port whatever. I have DAT running on port whatever, or Hypercore running on port whatever. I have, I don't know, HTTP for some web-based interface running. So they can announce via multicast IP addresses using multicast DNS, and then on top DNS service discovery. It's all many standards, but they kind of integrate with each other. I'm Jannis laptop and I have that running. And then all other devices interested in the local network automatically, as long as they're interested, receive this information efficiently and know that there's some random device called Jannis laptop in the local Wi-Fi having DAT running and connect to it. And this is how Chromecasting works. This is how AirDrop works on Macs. This is how DAT finds each other, like DAT replication, hypercore replication finds each other in the local network. This is how this Sonos music streaming works. This is how, if you have some kind of smart home app, it finds your fridge on the local Wi-Fi, and so on. Like all this magic, let devices find each other without manual configuration is usually something like this, or exactly this. So this is cool to play around with. There's many command line tools. I'm really not going to explain them because it's complicated. They have many flags that I would have to explain, but you can play with it. This DNS SD is available on Mac as is, and on Linux you can just install it. And you can announce as a test a random service that you can just make up, like foobar service, and then on another machine look for a foobar service, and it will magically find each other if the Wi-Fi network allows it. And this is also like, this is how your P2P application can find local peers, because usually the local Wi-Fi connection is much faster for replicating than going via the internet. The connection via the internet is usually as fast as you pay for, so usually the limit, whereas the local Wi-Fi connection is really as fast as the Wi-Fi devices are. So nowadays, pretty fast. Yeah, I don't know. There's many other things, but I guess we can stop here.
Do you use all of this for your daily job, or is this just like a hobby research that you learned all of this?
Half. Like this local thing,
Sending
I learned
data and so on.
sending data actually it's part of my job to do like networking stuff. You have one server and you have another. Oh yeah, like practical debugging, right? You have one machine and another machine, and they don't replicate via DAT or via whatever. Really doesn't matter. BitTorrent or some P2P thing doesn't work, or you can't Chromecast, right? So the first thing would actually be, first step would be finding out its IP address. Hopefully you obtain that somehow using this magic thing that I just explained by asking the device what IP address it has, as I showed. You can also scan the entire network. There's multiple ways. Let's say you know the other device's IP address, and then you could do many things that are really practical for debugging. So before I send this to Nora's laptop, we can check if Nora's laptop still is available by using ping. Nora's laptop is available. with an enormously high latency latency. This is not a good sign, Wi-Fi wise. Should be something like this. And if that doesn't work, you know that there's no IP packets basically going via the devices. So it's not that's fault, it's not some latency problem, there's nothing going through. And then you know the Wi-Fi is to blame, kind of. And if ping works, you would usually do some kind of NAT thing, and then you know that TCP works, and then you would do something on top. So you kind of go up in the layers, debugging. Yes, this works, this still works. Okay, this does not work, and you can somehow like limit the number of possible problems this way. And this is what I do quite often when like debugging problems. For example, there's two servers and they cannot reach each other, and then I figure out, is it like a configuration problem or actually the network underneath, if you will, that just doesn't let IP packets through. So yes, this will work, and this magic devices find each other thing, because I was curious how it works and because it's cool, like to have built something that magically discovers another device next to you. It's somehow like a cool feeling to build something like a chat that works entirely locally. I built that, and it's like at some point it's like 200 lines or something, and you have a chat working locally.
This was super cool. I heard a lot of talks about this stuff, but maybe because we did this practical thing, it kind of now at least feels like maybe I will remember. Thank you for this.
You're welcome. So if you want to exactly, if you want to play around using JavaScript, I mean, obviously the same is available for all the programming languages because it's a very common thing.
And probably also from other people, just not just mathematics.
Probably, but if you specifically want to use this magic announce yourself on the network with some kind of service, and as another device discover that someone has announced themselves thing and want to build something, let's say a local first chat app, then you were to use this library, and this is pretty much how devices find each other, like these 10 lines, 12 lines, 15 lines. So there's lots, like all of the components are available as individual libraries that you can use. And the NAT thingy that we did was plain TCP, right? I explained IP, and then on top TCP, and NAT is usually for building TCP pipes or garden hoses if you want. And the API for doing that in Node is the NAT API. So you could create a new server. This would be the netcat listen equivalent, and provide a port. And you would create, on the connecting side, create a net.socket. And this would be then connect to this other device. So we could have done the exact same thing as netcat with Node. It would just have taken longer and have, I guess, me doing mistakes, but it works the same.